Hello everyone, this is Dilleswara Rao from Aeronautical department. So we are in a way of right doing some classes on automatic control of aircraft. So last few classes we have discussed on displacement of autopilot and control augmentation system, stability augmentation system, its significance and its application also we already given in last classes. So now we are discussing on this modeling of control system. Actually, that modeling of control system, if you see this one, it need to be like a complete representation of any system, like maybe that mechanical operation system or electrical system or maybe that electronically operated system. That how we can design a control system that will be exactly matches the operation of a system which have been given by the designed input and required output and by giving a frequent input and what for that given input how that output signal is being completely given to that system and with that output signal how that system has been operating. So that we already seen in last classes like stability augmentation system and control augmentation system, how that things have been generally designed. But here we see actually what is the background of that system. So let's go into topic. So we'll see like generally we look at on most closely the continuous time that state space model and their properties and how they have been derived from the physical system and that the system that has been having algorithms for algorithms made for the computer can be applied to that any tasks associated with simulation of this aerospace vehicle or mechanical systems or thermally operated system or electronically operated system, electrically operated system, and other design systems also we can made it. We are using this controlling subsystem. That software tools like generally we will one while we are designing a control system that will be generally depend on how that system control is being designed by using desired input and output values. So here the software tool will provide the capability to trim the aircraft models and for steady state flight and perform a digital flight simulation and extract linear state space and transfer function description of aircraft models and to perform that control system design how we need to mathematically design that system and after the design of the system is being mathematically approved, how it will be going to that computer system, that will be the secondary case. So here the if you see two functions that has been like we said, any mathematical system that has been need to be uh, designed mathematically. So here the two mathematical equations that has been having variables of x and u, so that the function of x and u and x also having a function of n cross 1 and u is a function of m cross 1 and another function y, so that is g of xu and that y is also a function of p and p cross 1. So where that f and g represent the continuous and single valued functions, that variation of equation generally we can make it like take any variation example. So that is x dot will be equal to ax plus bu and y will be equal to cx plus du. So here you can see one linear equation we've been maintaining. That linear equation only will decide how that variables have been variables are changed with respect to that given function. So the behavior of a real system can be simulated by solving the nonlinear model equations. So the mathematical theory of numerical solution of ordinary differential equation will be the will be in the state will be generally be represented in a state space conical form. So here you see one algorithm that has been designed for general representation of systems. So that is like that is having that steady state transformation system transformation function is will be there, that has been installing installation, and after that non-linear simulation have been done. So that non-linear simulation and linearization and control system model also been integrated with that total function transfer function system, that is the nonlinear state space model of given function. So suppose if you see that two functions we have considered for here is that x of x dot and y dot. So for that system, the integrated systems will be this state space system and nonlinear simulation system and linearization system and control system design model also we've been connected with this one. So after that, once the integrated system has been operated by having the inputs from all these systems, that system will have an output will be like a linear state space model. So because if it is in a complex is, functions, so that complex function will be made it into one linear equation. So that may be that algebraic equation, or maybe we need to have a quadratic equation also. If it is higher order equation also, we need to derive that equation and get the variables, whatever the variables having the values from that function, that variables will be the linear design technique. Like once the variables we found, that variables will be the output of that function. Generally we can say like that. So here therefore, that state space model is a prerequisite for simulation. So the real system can operate around the design points that are the equilibrium conditions and are non-linear varying degrees, and as they deviate from the equilibrium condition. So by the linearization of this entire system, the new non-linear model around this design points may be powerful tools of linear systems theory, and that can be used by analyzed by system performance and the system design. The that state space formulation of lends itself to linearization around that equilibrium points only, because that state space formulation will be generally depends upon that linearization equation only, and that the matrix formulation of linear system state space equation is readily handled by multiple input multiple output systems also, and a single input single output system. And there will be like MIMO system can be generally be used in aircraft, some aspects of aircraft dynamics. So lastly, in addition to the equations that have been coupled to that model, the simulation, by simulating a aircraft control system that has been controlled easily designed by having the controller equations also in state space form only. So let's see what is this state space model actually. First, how the state space model has been used for making that design of control system. So generally, that order of ordinary differential equation, and our most powerful method for solving this equation will be the continuous time lapsed parameter dynamic system. So that continuous time lapsed system will be uniquely defined for all movements within the specified except specified interval, except possibility at a countable set of points. So that lumped parameter system generally implies on interconnected elements that have been make up the model response and immediately to the excitation. So this is in contrast. This is in contrast distributed parameter system, in which the disturbances propagate through the system's waves only. So the distributed parameter systems can be generally described by the partial differential equations only. So the real dynamic system can be have a lumped and distributed parameter system depending upon the frequency spectrum of excitation only. Like you see here, the lumped systems we are depending upon the lumped parameter system, and that lumped parameter system how that variables have been using for making that output signal will be having a frequency spectrum, and it's depending upon its frequency spectrum and excitation. Like you see previously, the output signal have been that output signal we have designed through its frequency response, like how that frequency response have been connected, and due to that frequency response we have an estimation like that system will be behave like that, and the aircraft will respond partly as a distributed parameter system to a sudden wind gust that excites the flexible bending modes of the wings and the fuselage. So for the wind disturbances that are less abrupt, it will be respond according to our rigid body equations of motion. For large flexible aircraft such as passenger jets and flexible modes can be low enough in the frequency approach or to overlap that rigid body modes. Generally, that rigid body modes means we have a fixed wing aircraft only. We are because every aircraft, whether maybe the passenger aircraft or jet aircraft, generally it is a fixed wing aircraft, but there will be due to this disturbances in system, so there may be mechanical disturbances also will happen, that is due to that fixed wing thing, and that fuselage bending modes also we will consider. So for the wind disturbances, like if you generally flying body means will have a disturbances from the wind only, so that will be if it is a less abrupt, that will respond according to the body equations of motion only. For a large flexible aircraft like passenger jets, the flexible modes should be low enough to approach that rigid body modes will be more sufficiently to make that design. So that state, suppose you have a idea of like we can describe this thing like we are going theoretically, but if you have a some practical thing like how we will design this general state space equation. You see some one mechanical system that has been having one spring and spring mass system that is having the spring and damper is being connected to that mass, and that mass is being connected out other side through a spring and damper system. So here you see that the spring displacement will be ut, like when the displacement generally we will see it in frame approach also in terms of u, and the output is displayed at y of t, and the mass is m, and that there will be like friction is generally friction in between here, it's generally we'll consider as a negligible thing. So the damper also will have a no mass, and only the displacement and dissipate energy thing only we will consider. So to produce the required force equation to equal to that viscous constant, that di terms the rate at which they are extending or contracting. So the auxiliary variable WT is needed to be the associated spring and damper. So there will be like that displacement, like independent energy storage and the systems can be assigned according. Energy storage can be right in terms of that x dot will be the energy storage. Then that x dot will be equal to u dot minus x3. So that will be like x dot we can say like it's a dot means it's like a differential function only. So that is that d2 of x3 minus x dot equal to k2 into x2. Then that the x3 that x3 will be equal to I mean, for a damper equation, that secondary damper, that sorry, that here we have seen like these are all three separate functions only. So first one will be that due to that displacement. So there it will be x dot equal to u dot minus x3, and that's secondly the damper thing. So due to the damper, that x3 minus x2, that energy between this spring and the damper will be equal to that kx2, that spring stiffness coefficient into its displacement x2. And that third one will be like with respect to mass. So that mass x3 will be x3 dot will be equal to k1 x1, that is for with respect to that first spring. And that damper displacement will be u dot minus x3 minus k2 x2, like k2 x2 will be the second spring stiffness matrix. So that will be I mean, we have three equations, so that three equations we can reduce in terms of constants that has been given here. X dot equal to ax plus b1 u dot, and further we can reduce like z equal to x minus b1 u, and then that z dot we can take it as a ax, and that will be equal to az plus ab1 xu, like z, if you say take it as a b1 minus x minus b1, then that x will be equal to z plus b1 u, right? If x equal to z plus b1 u, uh, 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 B1 u. So if you substitute there, we will get that z dot will be like ax, and that will be equal to az into ab1 into u, right? So like you see, the things will I mean, we have a state space function in terms of x and z. Suppose for a electrical system. So suppose for an electrical system, if you see here, there is an energy is been the voltage energy is been connected through one capacitor and a inductor and a resistor circuit. So here that capacitor C1 C2 is there, when one inductor is there, and R3 and R1 R2 and R4 are placed here. So for this electrical system, if you want to make this entire system represent in a state space condition, so we have the A and B matrix elements, and Aij and Bi, and the bridge tree circuit as shown in figure 2. Like if you see here, that circuit has been given here, no? So like in the figure, state variable will be x1, x2, x3 will have been assigned to that capacitor voltages and inductor current. So imagine a unit step voltage has been installed on that one. I mean, step voltage is given to that. So that series that generator is been placed in series with the C1, and as indicated by that dashed circuit, and let that for a time zero plus. I mean, if it is a time is increasing from 0 to some other level, the generator has been switched from 0 to 1 volt. So then at t equal to 0 plus, then x dot x1 will be like 1 comma 0, and x2 will be at 0 0, and x3 will be at 0 0. Like these are all changes in that function only. So, like you see, for a capacitor charges, that during the capacity charges, that I1 of I1 at 0 plus seconds will be equal to C1, that capacitance into x1 dot of 0 plus, that will be equal to C1 A1 A11 x1 plus C A1 x1 of 0 plus second. So then the A1 we will get it like I of 0 plus by C1 x1 of 0 plus. So that will be reduced like generally that at a 0 plus seconds, the total capacitance, like even we can write it like 1 minus 1 by R1 plus R2 R3 by R2 plus R4. Like you see, when that series function is there, then R1 plus R2 will there, R1 plus R2 will be there, R3 will be there. And if it is a parallel function, then that will be like 1 by R1 plus 1 by R2 plus 1 by R4. So then that thing will be like what? R1 plus R2 R4 by R2 plus R4. That is in parallel condition. So then for the same thing, if the voltage is being increased on the inductor at a 0 plus seconds, so that voltage will be equal to that L of x2 0 plus, and that will be like here we got a another variable, that is A21 will be equal to 1 by L of x1 of 0 plus seconds. So that will be like 1 by L means inductance. So that that means that A21 will be having 1 by L1, and for A31 like another value with another capacitance C2. So there C2 will be having two series functions and one parallel function. So that C2 into R1 plus R4 R4 plus R1 R4 by R2. So that means R1 R2 and R4 are been parallel function. So that will be like R1 R4 by R2, and that R1 and R4 are in series function. So that will be R1 plus R4. We got it. So like here I'm saying I'm not giving a much introduction. I mean, I'm not talking about how this electrical function need to be precisely. We need to take care, and series functions and parallel functions they should be like that only. I'm not telling that, but the general representation, like mechanically how that representation we got it, like for electrical equations also there will be one representation will be there. So that representation of equations only we are telling here. So that in second and third columns of A matrix, like A matrix, if you see it on, if you remember that equations of motion, A matrix will be S equal to, I mean, A equal to Si minus B is there, no? That mod of Si minus B. So on that A matrix will generally putting up a unit step current generator in parallel L and with a capacitor C. So the same manner the B matrix also can be found out by that voltage E of t and unit step voltage E of t with respect to that unit step voltage generator. So that the C and D matrix will be found out from same wave only. So like here the voltage will be equal to x2 plus C2 x dot 3 into R4. Like for this loop, for this loop, if you see that x1, x2 are the currents charging on, the currents charging through that variable. So we can write that V0, V0 voltage generated around that R4 will be equal to IR. So I will be equal to what is the currents in that direction will be like x2 plus x3 through that x3 through that capacitance, and R4 will be the resistor at that another loop. Like a closed loop, we will start from starting to ending like that. So that while we got that states function, like a different function we have for a mechanical system, that in terms of x dot and z dot we got two functions. For electrical system we have in terms of voltage and generator EMF values also we got like that. So we got this equation in terms of differential thing only. Now we will make this differential form into linear form. Like we said, no, that the state space model means what are the differential equations we will have. That ordinary differential equation will be converted into linear equation. That may be like a algebraic equation only. After solving that algebraic equation, we will get the values for that one. So here we consider that ordinary differential function, suppose like having a second order function, that is y star y double dot plus f of y dot plus g of y will be equal to h of u. Suppose you consider a equation differential equation like that. So then if you integrate that equation, that y will be equal to y dot d and dt, and y dot will be equal to like what, y dot will be integral of h of ut. I mean, if you want to say that y dot integration, so that h of u minus f of y double, I mean f of y dot also will be included on that, and g of y dot g of y also will be included on this integration. So the variable y may be the example of a position variable only. So the function of a function form of solution in the same will be used in any other quantity which have been analog of position. In an analog computer, a device is available to perform an integration of voltage with respect to the time, and the voltage is the analog of whatever the physical variable we wish to simulate. So we can make a diagram with respect to that analog computer conditions. If we draw a box representing an integration operation, like we said, we have an differential equation. Once we need to make that differential equation into algebraic, so we can use that. First, we need to reduce that differentiality. So once we reduce the differentiality, that differentiality will be reducing and make it into linearization. So here one representation, we make it like an integrator operation, and that simple symbol have been represented like two integration operation have been given here. So the I mean that summation of multiple of variables, like here you see that summation of multiple variables, this f function and g function. So these f function, g functions also additional functions of that input function only, that the variables are subjected to each operation, and that that thing will show like that analog computer is being connected in such a way that it is being switched with the correct initial conditions of that integration, that we can solve that equation 1 and 2 with respect to that integrated form. Like you see, for this integrator, there will be two inputs like y dot of g, y dot naught, and y of naught. So that will be the inputs for that integrator, and the integrator functions are fg and f and g, and that h function will be that constant function. So this can be like a this is like a single input, but the output also here we are getting single output, that to y. So single input will be u, and single output will be y. So that SISO system simulation will be having two integration with onboard I mean with that functions f and g are being connected to that summing amplifier. So with that summing amplifier, how that integrator will be solved, and from that integrator solver, what are the output parameters we will get it. So like this way, like we have a general equation, that general equation will be in a differential form. That differential form will be having several functions. That several functions will be converted into algebraic functions or linear functions by using an integrator. With that integrator, we will get the output values generally. So for that representation only, we made it every modeling system will be like this only. You see previously that SAS system and CA system and displacement autopilot system and control augmentation I mean that acceleration autopilot system also, everywhere we are seeing this integrator. What is this integrator? Why these outputs have been coming, and how this integrator has been designed? So this will be the basics of that work. So like how that integrator is being designed, and why this integrator is such a important function for making that equation will be very feasible. So here that if you see that figure, so that we simultaneously break the input connections of that integrator, so that if an analog input having the connected to that single ground, though the output of that integrators will remain constant at values they have where they had at the instantaneous of breaking of connections. So if the communication, the continuous input signal is been available, the analog computer simulation can be restarted at any time at all signals at all signals. So we can assume that values they had when the connections were broken, and the simulation can continue with no information loss. So therefore, the integrator output variables satisfy our earlier definition of state variables. So knowledge of their values at any time instant, together with the input signal, completely defines the state of system only. So now you see that right hand of previous figure 4. So there will be that x1 and x2 that has been defined as the integrator inputs outputs only. So that equation 2 for the state equation for above system can be represented like that x1 dot will be equal to x2, and x2 dot will be equal to the functions depends upon that variables, that is h of u minus f of x2 minus g of x1. So these will be the state functions, state space functions for this representative equation. So when the ordinary model may be involved derivatives of input variables that will be linear with the constant efficient, as the following second order example. Suppose another example having that second order differential equations are there. So that model equal to unity by dividing all other coefficient. Let the operator Pn indicates like Pn indicates a differentiation in n terms with respect to that time, and write the equation with respect. I mean equation for this double integration. I mean that double differentiation, second order differentiation function. So you can write like this p square p square of y minus b2u minus plus p1 p into a1 y minus b1 u plus a naught into y minus b naught into u will be equal to 0. So then if we integrate the dual times with this equation, so that after applying the integrator, the equation will be like that. So you can directly see in on screen also. So that the example can be extended in a general case of nth order differential equation. So with all the derivatives of input present, the differential equation can be write it like that p power n y will be equal to summation I equal to varies from 0 to n minus 1. So that will be like ai minus ai pi y that will be equal to summation of I will be varies from 0 to n. So b1 I p per pi u. So I mean we wrote that equation in a summation terms. So the equation we generally that equation we have it in that summation form. That summation form will be will be in having that variables, different variables also been installed here. So another things like time domain solution of LTI state equations, like linear time invariant solution. So this LTI solution can be solved like for this one model representation we have given here. So that has been shown in figure. So that will be having a one summation summing amplifier. So generally that the summing amplifier we will write it like this, and one integrator, and having a one this will be generally we call it as a feedback amplifier. So then that will be fed into that another function, and after that function another summation function may be there. So, I mean that output will be given to another summing amplifier also will be there. So here that state equation for this LDA can be solved analytically. That you see that elementary equation shows that the linear first order ODA can be solved by exponential integrating factor to yield an exact derivative. So when the equation will be solved by using invariant integrating factor, that will be reduced to simple exponential function. That simple exponential function you see, suppose e power at is there, so that exponential function is having uh, that explanation will be like explanation will be like I plus at plus a square t square by 2 factorial plus a cube t cube by 3 factorial, like the expansion for e for ab, generally we'll write it like by using that quadratic equation. So this series maybe if you differentiate this series with respect to time, so that d of AIET will be equal to a into e power e power ax will be equal to a e power x, right? So like that, that a into e power at. So if you integrate that e power at, then it will be like integrating that e power at. So that integration will be like what, e power ax minus 1. So we can write it like I. I mean, if you want to make it in, we are making in matrix form. So here it will be in terms of 1, we can write it like I. So then that a e power at will be equal to like e power at into a also. So then if you differentiate that equation with a additional function like e power minus at of x of t, so that e power minus at of x of t, if you differentiate that differentiate function will be, we can write it like e power at into b u of t, that x of t will be having a variable that has been converted into b u of t. So the integration, that integration of this initial condition at if you integrate that equation at by applying that integrator t to t naught to t, so make a having a initial and final condition t naught and t. So if you integrate the above equation like e power a into t naught t minus t naught, like t will be like t minus t naught, and x of t naught will be plus integrating t naught to t e power uh, t minus tau into b u of tau. So like this is tau will be like some change in temperature only. So that recursion formula, like here you see that recursion formula will be the practical for considering the time interval tau. So over which the input can be approximated by simple equation. So the discrete time formula by considering the interval from t equal to kt to t equal to k plus 1 t. Like we see from t naught to t, if it is having a function with changing with respect to k constant, like k constant means what, n1, n2, n3, n4, like that. So there will be an increment. That increment variable is with k only. So if you k plus 1, k plus 2, k plus 3, like that, increment is being given to that time variable. So that k will be like a positive integer, then that t naught will be like a kt, and t will be equal to k plus 1 t. So that will be like having a separate variable. So we can write it like a we can represent it with lambda. So then the above equation will be like what? So x of t, that means that t level, that is k plus 1 of t will be equal to e power at into x of k plus e power at into integral of 0 to t e power minus a lambda into bu into lambda of lambda plus kt of d lambda. Like here everything we have make it in a single equation, that has been representing with lambda. So the integral equation can be having we can solve by using a variety of method, like a trapezoidal rule or Simpson rule we can use. So we'll see that the simple stepped approximation for solving that u of t. So that will be like u of if that change in that t will be like lambda plus kt. So that will be if further change, that change is very less. So that will be almost equal to u of kt only. That means 0 lambda is changing from 0 to t only. So that is I mean here this function lambda will be called it as a zero order hold. Like zero order hold approximation means what? Already whatever the approximation we consider for the time change will be having a limit. So that limit we have neglected here. So that u of kt can be taken out of that integration, so that the remaining integral can be evaluated by considering that term by term integration of matrix approximation. So then that equation will be converted into x of k plus 1 will be equal to e of at into x of k plus q of t into v of k. Then that q of t will be write it like same explanation expansion theory only we have considered here. So that will be in terms of t. So that I plus at by 2 2 factorial plus a square t square by 3 factorial. This is like e power at formula only. So then the q of t will be equal to a inverse e power at minus e power at minus I. Like here, that a inverse will be like I mean, if you make that a matrix divided with that one, so that will be like a inverse into e of at minus 1. That e of at expansion also we see, but integrator for e of at will be equal to e of at minus I. So that we have wrote here. So that discrete time recursion formula, that alternative numerical integration of that state equation can be like linear and exponential AIT, like e power at, that has been found analytically or numerically. So that matrix exponential function is called it as a that e power at is called it as a discrete time transition matrix. Like here a is a matrix, matrix. So if a e power at matrix can be write it like a discrete time transition matrix. This will be the things regarding that control system I designed with. I mean, by following this general systems, like how that general systems will be. Here, what we learned is like how a mechanical system or electronical system or thermal operated system or maybe any actuated system or anything. First of all, we need to represent that in a mathematical form. That mathematical form definitely will have a differential equation, because whatever the theoretical background we learned in mechanical subjects, most of them are depends on that numerical equation only. Suppose if you see for a mechanical system, that energy equation, and like if you want to talk about that simulation, that the simulation generally that the fluid flow simulation will be mostly depending upon that continuity, momentum and energy equation. That continuity, momentum, energy equations are mostly depending upon what, that differential equation only, right? If you see that the derivation, you can have understood. So that equations are in differential form, but anyway, computer can take that differential equation, but the converting that differential equation into algebraic equation, from that algebraic equation into that real time variables. So we have a lot more things, numerical things have been depend on that. So this lot more numerical things have been I mean, if you want to solve that numerical equation analytically, pages and pages and white papers will be go on, and days of time also will go on. So that's why we introduced a computer for solving that equation. So after solving that equation, whatever the output, that only the important thing for us to control that thing. Like output is important for us, but for controlling that output and for giving that desired output, what is the required input also we need to know. No? So for that case, we introduce this electronically operated control systems. That control system will have electronically operated integrated circuits will be there. That integrated circuits means what? That integration function, because while you want to solve that differential equation, you need to apply that integration. Once you apply the integration, the double integration is double differentiation. The higher order is become single order. After single order, it is become variable. After variable, we are getting the value, right? So suppose that the integration of d square t will be what? It will be dt only. Again, if you integrate, what it will be? T only. That t means what? That value only, no? Like that integrator is giving the differential equation into ordinary value. how much integrator if you are applying, that much value, I mean that much accurately that value we will get. But that integrated design also will require many input variables. So that is all depend upon that how that algorithm we wrote for solving that integrator, how that values will be changing. So that is another case. So here our modeling systems are depend upon how to solve this equation. Whether if you are unable to solve that equation, like higher order equations or differential equations will having complex values, so there will be several rules also there, like that Simpson rule and the trapezoidal rule also we just seen, no? And after that, that LTI variable function, just now we said that LTI variable function also there. So like this, many things have been involved in this one. So even in our next class also, we'll continue with this only. That modeling of control system only. What are the different available systems for solving these things also? We will see it in next class. So that's all about this explanation. Hope you understood these things. So if you have any doubts on these things, you can refer this textbook, and you will have a great idea on this control system design. So that's all thing. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.